In 1991, after doing astrophotography for several years and having the same balance issues as most people, I wrote some instructions on how to balance an OTA and even advertised them in Sky and Telescope a couple of issues. But that venue didn't reach very many people, so I'm hoping YouTube can reach a lot more people and hope it helps. What I'm going to do is I'm going to show the problem on this telescope. The instructions are written using a 8-inch Newtonian, and I just use the same instructions from back then. And well, I'll look at that just showing the highlights of the instructions. I'm not going to go through the whole thing in great detail. Now, you can follow along. There is a link to a PDF in the description below, and you can print that out and check it out and follow along. So our instructions tell us to place the declination shaft horizontal and the OTA horizontal and balance it there. Looks good. Some people like to put it over here and check that, but I'll say that if it's balanced over here, it'll be balanced over here. And then our instructions say put it in the home position, we should be ready to go, but something's not right. What you've got to do is put the telescope vertical after this. And then you can obviously see this heavy guide scope is causing a problem, causes the CG to shift more from the center line of the tube outward. But we can't tell where because it's center of gravity is an abstract concept and the point is intangible. One way to solve this is to move your heavy objects in line with the declination axis, and that will fix the problem. But my point is here, if you can't place that there, or your heavier objects there, or don't want to place it there, then we've got to do some calculations to see where to put a counterweight. So back to a situation where we do have something heavier throwing the center of gravity off more than these lighter objects. We can only intuitively guess that the center of gravity is between the two center lines of these objects, but we can't tell where, but we know it's off toward this guide scope. Let me show you a little diagram. So here's some pages from the instructions. Ignore this one on the right for now, we'll get to that in a minute. But here, now don't change the channel. I know we've seen this a million times. I'm not going to spend a lot of time on this, but we've all seen the lever where you balance it left to right, and there's the math for that. But I want to point out that the center of gravity, even balanced across here, the center of gravity of this system is right here. So if we rotate the telescope upside down, this center of gravity now is here. Both of these are balanced, whether we put the telescope on one side or the other. But if we turn the telescope upwards, vertically, then the center of gravity is on this side, and if you let go, this system here, it'll rotate counterclockwise back to this position, finding its lowest center of gravity. So now that we've seen the problem, let's take a look at a few ways we can solve this. One caveat here is I just want to point out, I know we may have different terminology, formulas, and symbols when working with all this information. For example, difference between moment versus torque, and center of gravity versus center of mass, arm versus distance. There are differences, but I just want to point out we don't need to know the differences at all between these. I like the way Richard Feynman said it. He says, if you state the axioms, then the logic can be carried out without knowing what the such and such words mean. So I'm going to be using W for weight, A for arm, M for moment, and CG for center of gravity, because these are the conventions I used in aviation. But if you like different formulas and symbols, then by all means replace them with whatever makes sense to you, once you get the gist here. Okay, so glossary, we've seen the lever. This just shows where a simple diagram of where we need to eventually get the center of gravity to keep the whole system balanced. Another example of the lever, just using a telescope as an example. And when we get here, I've tried to put these in sections, so we're working on one thing at a time. This is the same as over here, it's just a little bigger, maybe easier to see. But we've got to take some measurements, and one measurement is the weight of these items and the center of gravity of the items. And while you've got the items off and you're weighing them and you're locating the center of gravity, find the longitudinal center of gravity balance point here and just put a mark there. We'll be using that later for balancing the telescope tube longitudinally. And then we need a measurement for an arc to find this angle here. And so to do that, just put a piece of tape along the side of the tube longitudinally and use a cloth measuring tape and measure on the surface of the tube around to a point on the surface of the tube where this imaginary line would meet the tube. And I know we're talking about the Newtonian over there, but just to show you here what I did on this refractor, just picked a spot there that was open and put a piece of tape, make a line on it. That way we can measure from this around to our a line that would meet the tube. And always measure counterclockwise for everything. Like the ASI air here would be at 0. Then I'd measure around for the guide scope, and then I'd go all the way around to measure a point where the center of gravity line would meet the tube here. It's rather intuitive, and you can do it this way, is just to take the weight and this arm of 7.5 inches, find the moment about this point of origin, and put a counterweight to counterbalance the viewfinder. You do the same for the focuser, and the same separate weight for the guide scope. And that's one way to do it. We'll talk more about how to determine the thicknesses of the weight a little later. And here's the original telescope we're working on. Hope you can see it from a 40-year-old photograph. But notice that this is, of course, looking from the top of the telescope. The guide scope here has a counterweight right here. Now it's hemispherical, but like I say, you can make the weight whatever shape you like. And this is a view from underneath the telescope. You can see the guide scope, the counterweight. This counterweight counterbalances the viewfinder on the opposite side of the tube. And right here is a flat, I don't know, 1/2 inch lead weight. And notice it is mounted between the rings. That way, when you loosen the rings and rotate the telescope to get it where you want it, the telescope doesn't slide forward and backward, keeping it balanced longitudinally. Another option you have here, if it better suits your needs, is you can calculate the center of gravity of the combination of these components and make one counterweight to counterbalance all of those. And here's how we get the measurements and what we do with them. So section 2, we plot the XY coordinates of each axis center of gravity. So for the viewfinder, I've got it written out here with instructions down here for the focuser. It's the same math measurements from above, just a little cleaner looking. Okay, so we need the CG radius. That comes out to 7.5. We need to find an angle from here to here. And to get that, you measure this length of arc. So we measure around the tube, we get 10 inches to this point. You take a radian times the length of the arc divided by the radius, and we get 120.6 degrees. And then we can find the coordinates for the Cartesian plane. Multiply the cosine of that angle by the viewfinder CG radius, and we get a minus 3.8 for the x coordinate. Multiply the sine of the angle by the viewfinder CG radius, and we get 6.5 for the y coordinate. So we express those as minus 3.8 and 6.5. So same for the focuser, CG radius 7.25 inches, angle 90.5 degrees. The x coordinate is 0. The y coordinate 7.3. I like to make a little table for all my measurements. So now we need to find the total moment for each axis. So the moment for x, very simple math here, comes out to be 148.6. And for the moment for y, 508.9. Then we can calculate the arms. So if we take the arm for x is going to be the moment for x divided by the total weight. So take that moment we got from above, 148.6, divided by the total weight of all the components, and we get 1.75. The arm is positive, so we plot 1.75 from the point of origin. And for the arm for y, the moment from above, 508.9, divided by the total weight of the components, we get 5.98. So plot up, positive 5.98. And we've found our center of gravity. But that is still intangible, and we need to make something tangible out of this. So, number 5, we calculate the length of arc to locate a point on the surface of the OT where a line from the point of origin to the center of gravity meets the surface of the tube. So, I'll be a little careful here. Let's use the inverse tangent function, and you got to reverse x and y here. Normally we put x and y for the coordinates. We're going to reverse them. We're going to put the inverse tangent of y divided by x, and we get 73.7 degrees. Now, this answer you get here may need modification because you might get a negative number here, and there's no negative angle. So if the Cartesian coordinates of the center of gravity are in quadrant 1 over here, then we don't need any modification. If the CG coordinates are in quadrant 2 or 3, then we add 180 degrees to this number we get. And if it's in quadrant 4, we add 360 degrees. So length of the arc, angle times OT radius divided by radian, we get 6.1 inches. So I've rotated this image here over here. I just wanted to show, so my X reference mark, X-plane reference mark here is rotated up a little bit, just to show that once we measure this arc from here around to this point and put a mark, then we have something tangible we can work with, and you can simply rotate that mark up to this point or down to this point, as long as it's in line with the declination axis. You don't need any counterweight for that, but if you want one counterweight, then we have to continue and find the distance to the center of gravity of the combined components. So simple Pythagorean theorem, but just eliminate any negative signs. We get 6.2 inches. So that is 6.2 inches. Now, you can start to eliminate, in other words, you don't need to see all these components here now. So just go back to the lever diagram. I find is cleaner, simpler. So we have 85 ounces at that 6.2 inches. So if we take the weight times the arm, we get 527 inch ounces. Now, I know this looks a little wordy, but, and you may not need to do this if you use a cubic volume or what have you, but this was using a cylinder, and is made of lead. So just showing how to calculate that out. A little bit wordy here, but we've got to have on the opposite side there, we got to have a weight and an arm, but we don't know either one. So we do some testing here. It's got to be some thickness over there. You're not going to put it inside the tube. It's going to be at least on the surface of the tube, and the weight's going to have some dimension. So take a guess at that dimension, an estimate rather, and say we have a 1 inch thick piece of lead. So half of that 1 inch is a ½ inch out to its center of gravity, is this imaginary weight. It's a ½ inch, so a ½ inch plus the OT radius gives us a 5.25 inch arm. And we take the moment from above and divide by that arm, we get 100.38 ounces of weight. Now, the volume can be found by dividing that weight by 6.56 ounces per cubic inch. That's the weight of lead. If you use steel, it's something else. We'll work on that a little later. And we get 15.3 cubic inches. Work your formulas for the volume of a cylinder. We need radius squared. So we get if we picked a 1 inch thick weight, it would come out to needing to be 4.4 inches in diameter. And that was a little big for my taste, so let's try 1.5 inches thick lead. So half of that's 0.75 plus the OT radius is 5.5 inches. So just do this again. It's the same formulas up here. Do it again, but make sure that you use the new radius there, because it's going to change things. So work that out, and we get 3.5 inches in diameter. So I like that. It's a lead weight, 1.5 inches thick, and 3.5 inches in diameter. So now, where do we put that longitudinally? Again, just use the side view of the telescope. This one's mounted in the middle. There's some choices you have there. All that information described here. But list all your components again. And notice that the secondary and primary mirror now comes into play here. Okay, because this view here, they were symmetrical about the point of origin. Didn't count, but now they are out on the ends of the telescope tube here. So you can take this all the weights and arms, get the total moments, and find the difference between the two total moments. Work that out and we get minus 2125.5 and 3232.0. And there's a difference there of 1106.5. So there's more weight in the positive direction, of course, because of the heavy primary mirror. Divide the difference in moments by the counterweight to get the arm of the counterweight. So moment divided by the weight equals 1106.5. And we divide that by our 95.66 ounce weight, and we get 11.57 inches. So if you mount the counterweight, of course in the minus direction, on the lighter side of this configuration here, mount that, and you can check your math here, but that minus 1106.5 plus a minus 2125.5 equals minus 3232, which now equals that side. Let's move on to the refractor. There are some blank worksheets here, and maybe you can just fill in the blanks and for your situation. I've just left the old Newtonian in here for a reference because I don't know what you got. And use what you need. You may not need all this. We're not going to need this part here on the refractor here. I'll show you why here in just a bit. Okay, so as I pointed out earlier, this is my line for the x-axis or plane. It happened to be right here in the middle of this, but it doesn't matter. Just it was an open spot. So we need to find the weight and for this telescope tube the radius is 2.467, and then I need a distance from the surface of the tube out to the center, and I get about 1.5. So 1.5, and then I need the arc, which in this case was 0. So 0. And then we move to the guide scope. The guide scope was 37.6 ounces, tube radius the same. Distance from the surface of the tube is about 3 3/8. So 3.375. When I measured this arc here, always counterclockwise again, I measured around the tube to this imaginary line, and I got 5 3/4 inches. 5 3/4 inches. Electronic focuser, it's 10.6 ounces at about 2.5 inches to its center of gravity. 10.6 ounces, 2.5. And for the arc, I taped it there because I only have 2 hands. Go counterclockwise all the way around the tube, and I get about 12 inches to this imaginary line from the OT center line out to the center of gravity of the EAF. You can see the measurements aren't difficult to take. You don't need micrometers and lasers, just and you can eyeball this stuff. Plus or minus 1/8 of an inch is more than adequate. So for the ASI air, I got 3.967 and 0. Guide scope -4 and 4.24. The EAF 0.75 minus 4.9. Work those out for the total moment for X and Y. Find the arms for each axis. We get minus 1.9 and 1.9. Note that that puts us in the quadrant 2, okay, for the next page. So now we're going to find a length of an arc to measure around the tube and mark a spot for the location of the center of gravity, radially anyway. I mean, we're not working longitudinally here. And actually I don't need to on this scope. I'll tell you about that later. So reverse this X and Y and we get a minus 45 degrees. Can't have a negative angle, so we're in that quadrant 2 at 180 degrees. Take that measurement, multiply it by the tube radius, divide by radian, and we get 5.8 inches for an arc. Measuring counterclockwise from our X reference mark around to about 5 3/4 and make a mark just for reference. Remember I said once we found this mark, you could just rotate the entire tube where that mark is in line with the declination axis, but I have a different circumstance here. Notice that this guide scope is not mounted on the tube, it's mounted on the rings. So even if I rotated this telescope within its rings, it wouldn't solve the problem. Like I said, you're just going to have to be cognizant of the possibilities in your situation. You'll see what I do here in a minute with the counterweight, the decisions I made. I'm still going to need the arm out to the center of gravity for this telescope, and I get 2.69 inches from the optical tube center out to its center of gravity. And I thought this was interesting. If you take that number and subtract the optical tube radius, you can see that came out to 0.22 inches. So in between the center line of the optical tube of the main scope and the center line of the guide scope, the center of gravity is almost 1/4 of an inch above the surface of the tube in that area. Anyway, that's always like to see what that really comes out to be. Did I cover that? Yes. Okay, so calculate the total moment. All right, so over here for our center of gravity of that tube, we got 56.5 ounces of total weight of all the components, and multiply it by the CG radius or arm of that center of gravity, we get 151.99 inch ounces of torque or moment about the optical tube center line. Okay, this is a mess, but I wanted to show you how you go through the mental gymnastics. I'm not using a cylinder here. I don't have the formula for the cuboid in the instructions, but that's easy enough. And so I'm going to use steel because I went out in my shop and I found some scrap steel pieces, and I thought, you know, that might work just fine. So I got to find the amount of the counterweight. So it's 152. I rounded that 151.99 over there, 152. And we take steel here. It's 4.537 ounces per cubic inch. So Here was my next trick here. I'm not going to drill a hole in the tube and screw any kind of counterweight to the side of the tube. So let me show you what I came up with. I'm going to mount the counterweight on the opposite side of this heavy side. You notice the guide scope is not mounted to the telescope, it's mounted to the ring. So just so happens I can mount it on the opposite side. There's plenty of mounting holes here, and straight across from there, this ring is 0.8 inches thick, and my counterweight I'm going to use, this piece of steel flat bar, is a 1/2 inch thick. This is how I handled that. So this sentence here, the arm of the counterweight can be determined by initially estimating a thickness of the proposed counterweight. I already know what that is. It's a 1/2 inch thick piece of steel I have available. Add that to half of that to the OT radius, plus the distance to a practical mounting surface. Well, remember my practical mounting surface there was 0.8 inches. All right, so half of that 1 inch weight is a 1/4 inch, so a 1/4 inch plus the 3.267 is a 3.5 inch arm. So now we got the moment of 152 divided by the arm of 3.5, and we get 43.4 ounces of weight that I need. Now, what's the shape? Well, if we divide that ounces we need by the 4.537 ounces per cubic inch, we get 9.57 cubic inches. All right, so how can we work that out with this cuboid? If I have a piece of steel, it's a 1/2 inch thick and it's 2 inches wide, so I know the width and the height. I need the length. How long of a piece do I cut to get that volume? The volume is 9.57 cubic inches. Divide that by 2 times 0.5, and we get 9.57 over 1 is 9.57. So I go out and cut a piece of steel that long. Here's my piece of scrap I found. It's a 1/2 inch thick, 2 inches wide. This stuff you can get at any box store, not that you'll use. And it doesn't have to be this length. I could have cut this in 2 and, you know, mounted it that. It doesn't matter. But I'd have to, if I did that, I'd have to increase that arm a bit, so it'd be less weight. So careful with that. I cut it at 9.5, close enough. And it has holes in it. It's just a scrap piece. It weighs out at 40.7. That's probably because I didn't quite cut it long enough, and each hole probably lost a little bit of weight, but it will work just fine. We're talking, 3 ounces. Let's see how we did here. So here was our original. And I will take our new weight. Mount it opposite the off center of gravity. And see what we got. have it. I know it's function over form, but that's the kind of guy I am. Now notice I'm not even getting to page 24 of the instructions where the longitudinal mounting matters. That's more for if you want to force the tube forward or backward in your rings. You can calculate that way. For example, this could have been mounted back here, which would make a back of the telescope heavier. So you'd slide the tube forward. Maybe that'd help your camera clear some tripod legs or something. Whatever, just trying to point out as many scenarios as I have available here to show. And that's about it. Good luck, have fun.